the microphone, it record and play, so something weird happened. Okay, anyway, so now if you can hear me, that's good. So before I start today's class, any questions?
Yes.
Yes, please.
How are the exams so far?
Exam grading more than halfway finished, but not fully finished. So I
How
don't
does
have
it
a
look?
full picture. Some did well, some didn't do that well. So always wish we can do better. By Thursday, we should have the grading score finished. Okay. On the other hand, me and the TA are a little bit sort of hold back debating how we can return the result to you, because some student in our class, because some health issue, has not taken the exam yet. So I want to just work that out, and then before I return the results to you.
Will there be like a graph that shows the grade distribution?
No, if you want that, I can ask TA, but I can inform you by Thursday what is the highest score, what is the lowest score, what's the median scores. Right.
Okay.
Okay. Okay. Any questions?
Professor?
Yes.
When are your office hours? I remember you said you were going to move them to a different time period because me and a number of students have a conflict in another class, but I haven't seen any updates on that.
Okay. I remember I talked to some students, maybe you, about the uncertainty. I want to walk through the uncertainty and then find a definite time, because at one point I wrote email to you and then talked to you guys in the class twice about we need to add the new lab sessions, and then a proposed time was Tuesday. So I want to say if we work out that time, I have to carefully schedule time. So one thing is that I intend to use Tuesday morning sometime to do the office hour. And so that I didn't get that through, and many of you didn't respond either. But I think, okay, correct me if I'm not right, the TH informed you yesterday, and the university department has worked out another option. So we will not add a new time, the lab session. So still we have the two sections, 9 to 11, 11 to 1 on Thursday. However, we opened another lab room so that students can spread into two lab rooms. One is the currently we're using IT 242. Another one is 238, just across the corridor. And that room is even a little larger, so we can put some student, half the student in 242, half student in 238. And if now we're trying to move the equipment, particularly the PC, and we have to activate the Ethernet in that room. And once the PC and table set up ready, then we can resume in-person labs. And hopefully, all this can be done today or tomorrow. So as early as this coming Thursday, we will resume in-person labs. But once I know for sure, yes, the labs time issue solved, then sometime later this week, I will send an announcement saying, put the Tuesday morning sometime as office hour. Okay?
So is the lab in normal time this week?
Yes, as a plan. Okay, if I call that a plan A. And this plan is still hinged on whether the equipment, particularly the PC, can be the PC can be moved to 238, but we want to make sure it connect to internet, everything work. So we're working on that today. Hopefully, I can get a positive answer. If not, let's see whether things can work out tomorrow or not. If by tomorrow we still have some issue, then I will instruct TA for this week. We'll continue to the lab online. If things work out, then the current plan is resume the in-person lab on Thursday. And TA should instruct you. Okay, I told the instruct TA, we will come back to 3 persons lab team, and some lab team have 2 persons. And if for 3-person lab teams, only 2 students will come Thursday, okay, in the lab, physical lab. One more student still will join remotely online. And mostly that group, 3-person team, will rotate on a rotating base. Some students will be joining online this week, and then some will join next week. A few teams, okay, for various reasons, students may still prefer to do the lab online, and then that 3rd-person team, the 3rd person will remain as online. So it's a complicated situation. We have to work through this. Yeah.
Professor?
Yes.
First off, so backtrack a moment. Office hours. So they've not changed. They are still running from 1 p.m. to 2 p.m. Tuesday, Thursdays as of now.
Right. Because I said initially I thought we will add one lab session on Tuesday morning. I don't want that to be conflict with my office hour. And that issue, I have to sort of settle that issue and then formally change the office hour.
All right. Apologies. I just wanted to get confirmation because I thought it was up in the air and that wasn't clear.
No, it's
that
not
said,
up in the air. I want the issue, if we can settle we don't need to create a new lab session, then a Tuesday morning is still kind of free. Yes, I'll put the time office hour on Tuesday morning. Yes.
All right. Also, thank you for informing us now, but I thought I'd just mention I don't have any such email from the TA explaining that there was going to be a new lab opening up. I just have an email from the TA asking for us to email from one member of every group to email him the names of everyone in the group. So I just wanted to say that you said they told them, said they evidently didn't.
So so what did the TA ask you? So in one team, who will be Thursday be remote? Is that what he's asking? That information?
He doesn't say why he wants the information. He just says, can one person from every lab group send their lab group number and all member name?
Oh, yeah, I can understand it's so vague. Okay, and then actually I instruct them to inform the student. The plan is if everything work out, we will come back the in-person lab this Thursday. That's really the important message. I said inform student our arrangement and then the plan. Basically alert you guys ahead of time, and most people will be asked to come in Thursday. Apparently, TA didn't do that. Okay, for whatever the reason. So, okay, after today's class, I will personally send that announcement to you. All right? Okay?
Okay.
Yes.
Yep, that's new information. Did not know we were going to be in person.
Sorry. This one is yesterday, I specifically work out the instruct TA and then say we walk through the plan, and then TA asked me whether should be list the team lab team, and then I said list team, inform the student the team new arrangement, as well as just say the plan is to come Thursday, but for whatever reason, he either misunderstood what I intend to ask him to do, or or there's some other reason, I don't know. Okay, any other questions? Okay, so basically prepare. Okay, 2/3 of people.
Sir, I have one more question.
Yes.
So, for the lab on Thursday, is it two people from each group show up to lab?
Right, because it's still, even with the two class, the lab room, we still cannot put all students in the room because of social distancing requirement. So
Okay.
we can only put one room, 242 is still limited to 8 students. 230A, slightly larger, can accommodate or occupied by 10 students. So say for example, 9 to 11 a.m. we have 25 people student. So only 18 student can physically come in Thursday. Another 7 student will need to join online. Yes.
Okay. Thank you.
Yeah. But the important thing is that inform Judith, and then TA will inform out of the 3-person teams which 2 should come Thursday, who will join remotely.
But the
We don't
TA
want
will
all
tell us
people
that?
come in, but then say no, you cannot get in, right? We don't want to create a chaos one more time this time, right? But TA didn't really inform you what's the plan and what's the rationale to ask you guys to come out with the information who will come, who will stay online. So, yeah. So basically, you asked the information, but you didn't know why that was asked. But you're clear now, right? Just overall picture.
Yeah.
Yes.
Professor?
Mm-hmm.
Just to make sure I've got the story straight.
Mm-hmm.
So every group's going to send 2 people, and in each lab, there's how many groups?
Each lab room, you say?
No. In every, because there's the 9 a.m. lab and 11 a.m. lab.
Uh-huh.
How many groups are in each lab?
Oh, 9 a.m., 9 groups will come. So together, each group will come 2 people. So 18 students. Then 9 groups spread. 4 groups stay in 242 room, and 5 groups stay in 238 room, just next door. Okay.
So we're not going to all be in the same. So that would be 20 people.
No, 18.
20 students, 2 TAs.
Yes.
I'm just asking because this is what happened
Yes.
last time, and I really don't want to repeat.
Right. Yes.
And you're saying how many will be in that room and how many will be in the other room?
4 groups in 248. So basically 8 students plus 1 TA. So together it's altogether 9 people. Okay. That room, 9 people. The other room is 5 teams. So 10 students plus 1 TA, 11 people. That room is allowed to up to 12 people. So we put 11.
So there's going to be 4 groups in one room and 4 groups in the other room.
No, 4 groups in one room, 5 groups in another room.
Okay.
Yeah. The other room is a little bit larger. So, yes. Okay. So I can tell you that the total occupancy limit for 242 is 9 persons, student plus TA. The other room is 12 persons, student plus TA. So we were operating just within or just at the limit of the occupancy level. Okay. Did I answer your question? Any questions?
Professor, I have a question.
Yes.
So, considering the lab is day after tomorrow, and we are not sure yet if there will be in-person lab, will you consider if some students can make it, as there is a matter of preparation to commute and all?
That's why I try to walk through the TA, and hopefully I asked them to send out the message to you guys yesterday, last night. So apparently there was some communication mislink, okay, created. What was your question? So we'll try to work out. Basically, you know that your teams, and then just 2 students will come, 1 student stay in the sort of. Apparently, TA was asking if you guys amongst yourself can work out who will come, who will not come. If we don't have this information, then I guess that's the last resort is I would just ask a TA to pick, okay, 2 come, 1 stay. So, but send the email to you.
But will you consider excusing if someone can't make it in such a short period of notice? That's what I'm asking.
Why cannot make it? I don't understand. Because you register this course, you know that's the time, and then we said that the in-person, when the time be ready, we'll come back to in-person lab. So the times of it that is there. So I don't know what mean by not available. Okay.
Okay.
Right. You know the time is perform the lab. It's just that time now. We will come back to UMBC to do something. Right. Okay.
Professor?
Yes.
So, first off, please understand, I'm not asking this to be rude or anything. I'm asking this because I don't want to walk in a room and get COVID.
I understand.
But you were saying that they haven't actually moved the computers yet, and they want to make sure it all works and the Ethernet and everything?
No, it's not. Moving the computer, TA cannot move it. We have to ask Jeff Weiss, the supervisor for all the department equipment guy, and his student assist to move the PC from one room, or say 5 PCs from one room to the other one. And
So it's not set up yet?
Huh?
So it's not set up yet?
They scheduled to set up today around noontime. But they have not formally write an email to me say everything works through smoothly. So.
Okay.
Right.
And let's say, something doesn't work and, I don't know, Ethernet's not working in that room or something. There's not enough table space to make sure that the board's actually far enough from the monitor. Will we hear about that? Will us first be hearing? Because we're hearing now. And we've heard nothing from the TAs, because you've kept on saying TAs will tell us, and the TAs continue to not tell us. Let's say that something goes wrong and, the room isn't configured by Thursday. How are we going to know to show up or to not show up Thursday? Because I don't trust the TAs actually going to email us at this point.
But maybe you have seen the communication manners, all right? So apparently every time I have important things to inform students, I go to the Blackboard announcement, and also that at the same time, I try to click send an email to the student inform, so that I know an announcement notification was sent out to the student. Apparently TA, I myself don't receive the similar kind of messages. So the TA has a different manner to communicate with you guys. So that's one thing. The question you raised, okay, I think I already addressed. All right, that room 238 is larger. And let me emphasize, it's larger than 242, and then it's identified. Okay, can put occupancy up to 12 people. And that room has tables, okay, are wrong. So we will set the tables, okay, including partners to separate the 6 feet. That's what I instruct TA. So altogether, probably 10 tables will set, okay, the 6 feet apart in that room, okay, for the 5 groups. So that's what I asked TA to do this today. And plus, once the table is set up, then the computer will be hooked up to the Ethernet. Sure. Those things should be manageable. Only thing a little bit uncertain is we don't know the Ethernet ports in that room functioning properly or not. Okay, so right now in my mind, that's the only thing.
So, Professor, I agree that I think it'd be great if we have the 2 rooms. I think that makes a lot more sense than 1.
Mhm.
But my point is, so the TA should have been emailing us like that we had lab in person this week, but they haven't.
I know. So that's
But
what I'm my
also-
surprise. You guys, or they didn't write a straightforward, okay, or the message is saying what's the plan for this week, right, to you.
But also, last time we had lab and we had the COVID scare and everyone had to run out and get a test, you said you didn't know that the TAs had decided not to split the lab sections in two, but instead put everyone in the room at once. You said that you weren't informed of that
I
either.
didn't say that. No, I didn't say that. I think you miscommunicate. That one was, it's not the two section, because the two section, you register your classes. Some of you know it's 9 to 11. Some is 11 to 1. When I say two section, I meant these two sections. And then the student came at a different time, those two sections. I don't think there was confusion for that part.
But there weren't two sessions. There was one session.
No.
You put 24 of us, or was it 25, all in the room at once.
See, that's your misunderstanding. There are 25 people registered in a single lab session. It is for the 9 to 11. It's not that there are 25 people are two section students. They're single section student. We just say the room was not enough to suppose to handle 25 students. To comply with the social distancing. So
yes, and you said you weren't aware of that at the time.
No, I will. What do you mean? I'm not aware. This starts with arguing. Okay, I don't know it's helpful or not. Because when you say the TA let the two section student coming into lab, that's incorrect, I just don't say. Because the two section means one is 11 to 1, another one is 11 to, one is 9 to 11, another one is 11 to 1. TA has no intention to put these two section students in single section.
Oh, no. Sorry, I'm not saying two sections to one.
You use the word two section student, right? So that's what I'm saying is that we're confusing, okay, or miscommunication. So understanding each other's what they really meant.
Well, apologies. I was referring to that there is 25, I believe, students in the 9 a.m. lab, and that my understanding was the plan was for that 9 a.m. lab to be split into two sections so that a group goes in and then they come out and then another group goes in. But my point, and apologies, I don't really want to argue about this because I agree that it's really getting anywhere, is there seemed to be some communication issues then as well.
We learn our lessons. That's why we're trying to work out a new plan. Why you want to use that instance to imply we are having chaos tomorrow, this Thursday?
I don't know. I mean, I hope you have, but
no,
I don't want to get COVID.
That's fine. We're trying our best. We're saying even a 9 a.m. student, only 18 students will come. Right? It's not 25 students come. 18 students will come. And these 18 students will come. A will walk to one room. Another 10 will walk to the other room. That's our plan. I don't see anything chaos will occur this Thursday. I don't know how you get the impression there will be another chaos this Thursday.
What I'm saying is there's chaos right now with the TAs having communication with us. And I'm saying I think there's previously been communication issues between you and the TA. So if there's an issue tomorrow setting up the lab, and hopefully there won't be and everything will be fine. But if there were,
set up today,
then how are we going to know there's an issue?
That's part of things I instruct TA, okay? We go plan A, as I explained, trying to explain, this is the audio, is 25 minutes into today's class. At the very beginning, I already said, this is plan A, current plan. If anything, okay, for unforeseen reason, didn't work out properly, like for example, Ethernet the port was not activated properly, then we'll cancel our plan. We'll go back this Thursday to online. And by tomorrow, we'll inform you. I already said that, okay, quite some time ago today, okay? Do you still have uncertainty of say what I just said? Our plan is a plan, right? But if this plan has some issue, so we cannot make it this Thursday, we'll change back to the online. And these things they will communicate to you by tomorrow, right? If something not work out. Do you have issues?
So long as you can make sure that we get contact tomorrow, should something go wrong, then I'm fine. That's it.
Right. So, okay. So I will talk to TA. Okay. I will personally send email announcement to you. Any other questions? Okay. If not, pick up where we left the last class. So last class we discussed the biasing. Okay. So for analog amplifier, we want to operate in a sort of a question point, operate in the middle of the forward active region. So that the middle is the question point here. And then you want this biasing be stay there even if the transistor property change a little bit, like say the beta value vary. So for that, we have to use a different scheme, like a circuit configuration to accomplish that goal. So that configuration is we call a voltage divider biasing. Okay, and so this is a circuit. And for this circuit, for DC biasing, we can neglect the capacitor, neglect the AC signal, just walk through the rest component. And for that part, first we will say, for the circuit seen by the transistor between the base and the ground, we'll replace this biasing part, the component, replace mathematically modeled by its Thevenin equivalent. So the Thevenin voltage in series with the Thevenin resistance is set between the base and the ground. Okay. Once theoretically we can remodel the original circuit by this configuration, then we can carry out the rest analysis. So on the left, first bullet just say what the Thevenin equivalent circuit is to be. So Thevenin voltage is the voltage drop at resistor 2. So once this part is a break, the open circuit. Okay, so that's Thevenin voltage is always the open circuit voltage between 2 points. So that between 2 points is at the base and then the ground. Okay. Thevenin resistance is when you deactivate all the independent source voltage source to the say voltage source is ground short. Once it's short, this point is ground. When this point is ground, R1 actually turn out to be parallel with R2. So we identify the value of Thevenin voltage and Thevenin resistance. So the biasing circuit is replaced by the Thevenin equivalent. And for this kind of configuration, then we can carry out the rest calculations that we have seen before, in early part of the chapter. So we derive this result. And we can calculate the base current and collector current. And here is the trick is, in this circuit, we will purposely satisfy this, the blue bullet part. The Thevenin resistance is much, much smaller than 1 plus beta times the emitter resistance RE. Okay.
Professor,
Yes.
I apologize. I think you mentioned this in a previous class. I'm just confirming. You
Yes.
said that beta will be given to us, correct?
Pardon me?
In a previous class, you mentioned beta will be given to us. Is that still?
Yes, beta is always the transistor property, just like the diode property, which should be given. Yes. Like
Okay,
yes. Like also the turn on voltage VBE on, that beta and this quantity should be known. Okay. And if R7 value is much less than the second term, then we can neglect R7 and beta over 1 plus beta. Beta is much greater than 1. 1 can drop. So the numerator's beta and denominator beta almost can cancel, so that collector current can almost simplify to this form in the blue formula. Okay, and this blue formula say that the collector current is not sensitively dependent on the beta, so it's a biasing stable. If collector current is not sensitive to the beta, then likewise, then the VCE, collector to emitter voltage, will also not be sensitive to the beta, so that the crescent point will stabilize, okay, at this point. So it's not because you change the beta, but then even you change the beta, then this point will almost stay there. So that's a biasing stable. Okay, we say R7 is much less than 1 plus beta times RE. How much less? Well, the general rule is, okay, you take about 0.1 times that factor, or 10% of that factor. Okay, so that's the rule.
One more question.
Yes.
Can you just rephrase quickly why we have 1 plus beta instead of just beta?
Oh, no. It's not I want or I don't want or arbitrary choose. This coming from the second bullet, the Kirchhoff voltage law through the base emitter loop. So basically through this loop. Okay. So this loop, there's a voltage drop at the resistance, terminal resistance through current IB. But there's a voltage drop at the resistance RE. The current amount is the emitter current. So IB and IE are two different current. But however, we know IE, emitter current, is related to a base current by this 1 plus beta times factor. So because this is emitter current, IE, that 1 plus beta coming from there. If the equation involves a collector current, then it's just beta times IB. But for the emitter current, it's 1 plus beta times IB. Okay? Did I answer your question?
Yes, thank you.
Right. Because this current is IE. If you're talking about this current, yes, this is 1 beta times this current. But for this current, there is 1 plus beta times this current. So it's IE there. So next, okay, to write the slide. Okay, I'll walk through a design example. Okay, this textbook is 5.16. And this design example is saying a number of quantities we know, and some of the quantities we don't know yet, but we will select that to satisfy certain requirement. So what do we know? The power supply voltage is known, VCC, and the resistor RC, let's see. Okay, VCC is known, RC is known, and the turn-on voltage, VB on 0.7 volts is known, beta value is given. Okay, so this known, okay. However, well, we put this way, this VCC is known, this RC is known, but we have not decided what values R1, R2, or RE are. So we want to select these three resistance values to satisfy certain conditions. So what condition we want to satisfy? We want the biasing circuit be stable, so we will use this configuration. And then such that the voltage between collector and emitter to be 3 volts. That's condition we set up. So once we set this requirement, so let's walk through how we can determine the rest resistance we need step by step. Okay. So previously we derived these equations for that circuitry, and now for the design process, it's kind of a reverse way to calculate that, but equation-wise it will be similar. The first step is, okay, another consideration is we put the resistor RE here, but we don't want a large voltage drop at RE because you use power supply battery voltage. You want this battery voltage mostly spent at the transistor. You add it for stability, but you don't want a large voltage drop wasted. So what do? We want the voltage drop at the resistor RE be not large. How much not large? Comparable to this base and emitter voltage, that's 0.7 volts. So we want this voltage comparable to this voltage. So that's what it is. So that just say, typically we set the voltage drop at the resistor RE, which equals the current times resistor RE, and comparable to VBER. And we also recognize the collector current, okay, and emitter current are almost the same. They differ by 1%, basis alpha. So that approximation we can take. So substituting this equation, say, what's the current, emitter current? So how do you calculate emitter current? If you approximate the emitter current and collector current almost the same, we can use Ohm's law. Use the top power supply voltage VCC, subtract the voltage VCEQ, and that's the voltage rest shouldered by resistor RC and RE. Okay, and that voltage divided by the resistance RC and RE gives you this current. So that's what the equation on the left. Okay, right is VBR. So we derive the equation. In this equation, all quantities are known. Basically, power supply voltage we know, and rest quantity we know. We know the resistor RC, and we also know the requirement for VCQ. Then I can find the value of RE. So I determine a one resistance value. The next,
Why are you locking the door?
Any Mike.
Okay, okay. So some student, next, we need to determine the resistance value of R1, R2. How do we do that? Well, we know the design criteria is such that we want to set the Thevenin resistance be 0.1 times 1 plus beta times RE. So that will say, yes, we want to satisfy this requirement. The step 2, the Thevenin resistance take the to approximately equal to 0.1 times 1 plus beta times RE. So that's one condition. The next condition is, okay, we want to find out what's the value we need for Thevenin voltage. But then the Thevenin voltage must satisfy this equation as we derived earlier. Step 3 says. In this equation, let's see, okay, term by term. Okay, the last term is the voltage drop at the resistor RE. The middle term on the right is VBR. And step 1, we said, I want this quantity be comparable to this quantity. So these two together should be 2 VBR. How about the first term? Okay, first term, R Thevenin. R Thevenin has a term 1 plus beta. 1 plus beta times IB is exactly IE to the left, the screen here. IE equal to 1 plus beta IB. One of the students asked that question, so we are using that again. So 1 plus beta times IB is IE. And IE times RE is another VBR. And you just have another 0.1, okay, fraction ahead of it. So you have a 1 VBE, this another VBE, and this 0.1 VBE. Altogether, these three terms add up. So it's 2.1 VBR. So this is another value we set up for the requirement for V7. And next, we use these two equations saying where's the V7 is coming from the voltage division from the power supply voltage. How about the R7 is parallel combination of R1, R2. We know the value of R7. We know the value of V7. Then we can resolve the value of R1, R2, which I put to the last two equations. So we can find out, identify the value of R1, R2. Any questions? So this is a design problem. In this design problem, assuming the resistance RC is given, okay, what if the resistance RC It's not given ahead of time, but need to be determined. Well, basically saying you need one more condition, okay, in order to determine the value of RC. And this condition is in the domain of chapter 6, basing from the from the AC amplifier. Then what we have certain requirement, say how much input resistance we want, or how much amplification gain we want. And so that's set up another condition. So we can formally design the transistor circuit for all the resistance we need. Any questions? Okay. In previous example, we used the NPN transistor, okay, in the circuit. In this example, saying, what if we use PNP transistor? Well, that's an example. So transistor is PNP. So the arrow at the emitter is pointing inward to the transistor. And furthermore, and it has a two power supply voltage. One's at the top, V plus, one's at the bottom, V minus. Again, we want to simplify the bias voltage between the base and ground to the transistor, replaced by the Thevenin equivalent. So as illustrated here. Okay, that's what we want to replace. Okay, the biasing voltage coming from the top power supply voltage up down to the base, and negative power supply voltage and down to the ground. All that replaced by the Thevenin equivalent. So question is how to figure out this Thevenin equivalent. First, Thevenin voltage. Thevenin voltage is the voltage when this part is open, and that's the voltage between this point at the base and the ground. The voltage between the base and ground is start from the ground. You come up to the point, this point, so voltage V minus, and you plus another voltage rise at the resistor R2, then that's your Thevenin voltage. So the Thevenin voltage contains two terms. One term is the amount of V plus coming from the ground. Another term is the voltage rise or voltage portion shared by at the resistor R2. And we can calculate that by voltage division. So what's voltage division? The total voltage difference at the top at this point and the lower bottom at this point is V plus minus V minus. So that's inside the parentheses. Okay, what's the portion showed at the resistor R2? And that's the front factor. That's voltage division. Okay, 306 subject. So by this, we derived the Thevenin voltage for this biasing circuit at the base. How about the Thevenin resistance? Well, we have to deactivate the independent source. Voltage is short to the ground, so this is the ground. And this voltage source short to the ground, this point also is ground. Then it's also against R1 become parallel with R2. So that's the Thevenin resistance. So this V Thevenin, R Thevenin will be modeled at the input end between the ground and the base. Once we divided this resistance circuit, we have walked through this example before, so it's a repeat. I will go a KVL, start from ground, go top to the V plus. So voltage V plus should be equal to the voltage drop at this resistance and equal to voltage drop at VEB on and equal to voltage drop at resistance R Thevenin and another voltage drop V Thevenin. So that's the second equation. V plus equal to voltage drop at RE and voltage drop at VB on and voltage drop at R Thevenin and another voltage drop V Thevenin amount. So this equation. Okay. So we know the V Thevenin, we know the R Thevenin, and we should know the relationship between RE and RB. And this equation allows us to solve out the current. Okay. Base current, collector current, emitter current. We can solve that. The last quantity we need to find out is the voltage VEC. But then this, using another KVL, we can solve that. Basing the KVL is a start from the ground, we go to the top, and going down, going down, going down, going down. Basing from the top to the bottom, straight down. It is Kirchhoff law. So V plus equals to voltage drop RE, voltage drop VEC, and voltage drop at RC, another voltage drop at V minus. Okay, so by this equation, we can work out the quiescent point value of a VCE, ECQ. Any question? Okay. And this is another example, okay, biasing circuit. We call it integrated circuit. Later, basically, a second diagram will later will explain that. Basically, in this circuit, there's a current source, okay, involved in biasing circuit. This current source, okay, connected between the emitter to another power supply voltage source. Well, we know once you connect the circuit to a current source, then the current in this branch is tied exactly to IQ. So what's this current? It's emitter current. So IE will be equal to IQ. Just really, you fix IE value. And you assume in forward active mode, once you know the current, the emitter current, then you can calculate the collector current by this factor. This factor, beta divided by 1 plus beta, exactly equals alpha. Okay. So we can determine, you know this current, then you determine this current. Okay. So we know the collector current, but what do we need to find out? The question point is what? What's the voltage drop between the collector and emitter? This voltage drop. How do we find this voltage drop? This circuit is really tricky, so I make it 2 steps. Okay, 1 step is I use a KVL, start on the ground, start from ground. Then there's a voltage, okay, drop here, and the resistance RB, which is IB current times RB, plus another voltage drop here is VB on. So after these 2 steps, where I end up at this point. Okay, hope you can see my mouse right at the emitter terminal. And I just use a symbol VE to stand the voltage at this point, between this point to ground. I call it VE. VE is between the collector, between the emitter and the ground. So that's KVL. Another KVL is I start from the ground, go to voltage rise, V plus, and this should equal the voltage drop at RC, plus voltage drop between collector and emitter, and end up at the same point at the emitter. Okay, so this voltage rise, V plus, equal to voltage drop at RC, plus voltage drop at the VCE, and end up at the emitter, and have another voltage drop VE get to the ground. I subtract these 2 equations. I use this equation to subtract this one. I end up with the last equation. So last equation, all the quantities I know the resistance values, I know VB on, I know currents, I know the power supply voltage. So by this equation, I can determine the voltage VCEQ. Okay, so that's the way to determine. So I use a 2 KVL to simplify into a single KVL. Okay, this is kind of say, a little bit sort of complicated. But you can visualize this KVL in 1 loop because it's a KVL. So what's the 1 loop? Follow my circle, the cursor. Okay, from the ground, I go to the V plus at the top. I going down, passing through RC. I going down, passing through from the collector to emitter. Once I get here, I shoot this way through the VB on, and then another voltage drop at RB. So that's the steps you can visualize. Okay, from the ground, shoot up, going through this part, going through this part, backwards going this part, backwards going this part. So you can derive the equation. So that just says if I use the illustration circuit, I can solve a quiescent point value. Okay, why we call that as the integrated circuit, okay, biasing is illustrated by the second diagram. You look at the second diagram, okay, and you see, I hope you can visualize there's some similarities between the two diagrams. So what's the similarity? Start at the top, V plus is V plus, and down through the resistor RC, RC. And next is NPN transistor Q0, Q0. And to the base, connect through the resistor RB to the ground, RB to the ground. At the very bottom is V minus voltage, at the very bottom is V minus voltage. What's different is what? The top diagram's current source really is replaced by or represented by this complicated structure. Or this, you can say complicated. Why complicated? Why not using a simple current source? What we're saying is, in integrated circuit, okay, we're using two transistors back to back, Q1, Q2, to function as a current source. So that's the name called integrated circuit biasing. In integrated circuit biasing, we are not able to provide a true current source, okay, separate current source, standalone current source, but we use two transistors to perform the function of current source. So we have this circuit. It's very complicated, okay, but let's step by step to go through that. First, KVL around the loop of involved resistance R1 and transistor Q1. So basically goes through R1, goes to Q1. So start ground, I go through R1, go through this voltage drop, and go through V minus, return to ground. So that's the first bullet equation. The voltage drop R1 plus voltage drop at VBE, this voltage drop, and plus voltage drop at V minus, complete the first KVL. And in this equation, bias voltage is known, the turn voltage is known, the resistance value R1 is known. We can figure out the current I1. This current I1 is solved. The second, okay, we use these transistors, and we want to make them transistor property identical. So the turn voltage between the base and emitter for Q1 equals the turn voltage between this to this equal to the same. And actually, the turn voltage is the same, and then their voltage drop is exactly the same because these 2 point potential exactly equal. These 2 points shared by two base. This point shared by the two emitter. So this voltage drop exactly equal to this two voltage drop. So that emitter voltage, base emitter voltage, the two transistors are the same, then the two base current are the same. And we can translate, okay, their collector current are almost the same, okay, because both are beta the same. Slight difference is that's slight difference because this voltage, okay, this biasing voltage, but voltage point between this point is 0, and this has a finite voltage. But that finite voltage influence very little. So while two base current are the same, collector current will be very closely be the same. So the last bullet says, okay, I have a KCL at this point. So that says what? I1 current equal to sum of IC1 current plus this branch current. And this branch current split into IB1, IB2. So that's this equation. And that's a little bit sort of typo. I should write is IC1 plus IB1 plus IB2. But nonetheless, IB2 equals IB1. So this is still correct. But then IB1 will be much, much less than IC1. So I can drop out these two base current compared to the collector current. So I1 equals IC1. So where's IC1 is here. So this current is equal to this current, almost. But then when we're saying these two transistors are the same, so this current is almost equal to this current. So IC2 equals IC1. So basically, IC2 current is tied to the I1 current. So that's your equivalent current source IQ here. IQ equal to IC2 and tied to I1. So this part of the circuit functions as a current source when using the two transistors. Any questions? Okay. So similarly,
Hold on.
yes,
You said IC1 is equal to IC2?
almost. Yeah,
Almost.
yes, I use slightly approximate sign here.
So what does that mean for us? Do we, in analysis, would we just treat them as equal?
Treat them as equal. Yes. But this is mathematically they're equal, but we're saying that two transistor property are the same, so their base current are the same. Then if the transistor property the same, means the beta 1 and beta 2 are the same. If strictly according to this relationship, IC1 should be equal to IC2. Okay? Here just a slight difference is because for the transistor 1, between the collector and then base is a short wire. So this voltage VBC1 is 0. However, for transistor 2, collector and base is not short. It's a finite voltage drop here. It's a 4 by, this is a reverse bias in this part. This is 0 biasing, this is reverse biasing. So it's a slight difference. So that's it. So physically, they're not exactly identical, but that inferencing is very small. So numerically, you approximate them equal. Yes. Did I answer your question?
Yeah.
Okay. So I cannot claim they are exactly equal. That should not be, but they should be very close. Okay. Any question? So no question. So we formally end chapter 5, DC analysis and DC biasing. Okay. The application of this biasing is what we have in mind, is the analog amplifier. So that's what this circuit is about. Analog amplifier. So analog amplifier, we want to biasing the quiescent point in the middle of this the forward active mode region. And then the input signal we coupled in can have maybe some sinusoidal swing. The output voltage will have some sinusoidal swing. So that's analog amplifier. So next we'll go to chapter 6, which can analyze different type for analog amplifier.
Is the amplifier how we is it the same as amplifying volume, like with sound?
Actually, good question. So we will get there. Okay, the amplifier sound is one application. That's audio amplifier. And actually, your project, the multi-week project, AM radio receiver, is you receive a weak electrical signal from antenna, and then eventually your amplifier, the current is strong enough, can drive the earbud or speaker so you can hear it. Yes. But that is complicated, it's not a single amplifier. Simple amplifier can accomplish that purpose. You have the multiple amplifier, to do that. And then multiple amplifier involves different type of multiple amplifier. And we will go through the chapter 6. Once we go through chapter 6, then you know the basic principle, and that basic principle will be used in your multi-week project. Okay? So,
okay.
Yep. Hopefully you're interesting and then really anxious to get to that part. Build the AM radio receiver yourself. Okay, this slide is a chapter 6 slide. Okay, I upload and you get that, hopefully. So, analog signal and linear amplifier. So first slide is basically highlights the important concepts involved. Okay, if we want to amplify the analog signal, we don't want distortion. Okay, we want to keep the fidelity, so that the signal, while it's amplified, must be linear proportional. Okay, every pass. All right. So you don't want to amplify some part here, not amplify some part there, then you distort signal. So you want to linearly amplify the signal, so that transistor must operate in the linear region, and that linear region must be in the forward active mode. That's the reason for analog amplifier we want to operate in the middle ground. And the second important concept is the superposition principle. Okay, I allude okay, at the first class. That important concept from 306 will be heavily used in chapter 6 here now. So repeat what's the superposition principle. So the response of a linear circuit, if it is excited by the multiple sources, then you can deactivate some sources, keep one source, you find out the response. And then if you add up the response due to different sources together, you get the total response. That's a superposition principle. Okay. Be more specific for our transistor linear amplifier to use this superposition principle is a third part. Third part is for the transistor linear amplifier. The first bullet is we classify the sources into DC sources and AC sources. So these are two types of sources. One is constant in voltage, one is changing in time, okay, the voltage. So for example, okay, you have a AM radio receiver, you need the power supply voltage, battery, 9 volts to power the receiver, and that's a DC source. And you also have a antenna receive the signal from the air. That's a time changing, that's AC source. But you classify them into DC source and AC source. So when you do the DC analysis or biasing analysis, you deactivate the AC source. So you only have the DC source, which determine the question point, bias point. So the second bullet. So when you analyze the AC signal analysis, you deactivate the DC source. When you deactivate DC source, you only left with AC source, which actually is your AC input. For example, AC signal from the air antenna. So this the source drive your AC amplifier as input, and after amplification, you get your output signal, get amplified. Enough volume, okay, enough current to drive speaker so you can hear that, right? So that's classification. And in chapter 1, we introduced the concept of the convention used in textbook, okay? Full signal, DC signal, and AC signal. Full signal, we represented by lowercase symbol and capital subscript. DC signal is capital symbol, capital subscript. And AC signal, everything lowercase. Lowercase symbol, lowercase subscript. Okay, assume it's small. So repeat. For example, I use base current to representing the 3 type of signal. So superposition principle applied to the DC and AC analysis has 3 kind of aspect, 3 angles to view it. One is the first, full signal mathematically equal the sum of the DC signal plus AC signal. So that's a superposition, strictly from the 306. Then in terms of circuit, you can separate it into DC portion of circuit and AC portion of circuit. And DC portion of circuit, how do you get it? You deactivate the AC source. And AC circuit, how do you get it? You deactivate the DC source. And the AC circuit really is the small signal amplifier circuit. Analysis will follow. So for the DC circuit, you do the DC analysis. For the AC circuit, you do AC analysis. Then you get a full response. Okay, last equation, just illustration for the base current as example. The full signal IB as function of time equals, it's a DC portion, capital IBQ, and plus AC portion, small IB. Okay. So this illustration, the circuit, okay, we have a transistor, NPN transistor, power supply biasing VCC, and another power supply biasing VVB. That's a DC biasing. And then if we imagine we inject the AC signal VI by this, okay, the pink, okay, voltage source. Right, this is a circuit. And we want to, okay, DC biasing location is in the middle ground. And around this ground, the AC signal can be amplified. go through the physical laws. Kirchhoff law. Okay, first. Kirchhoff law, I have two loops I can write. One is the loop at the bottom, say from the ground, goes through the voltage VBB, goes through voltage VS, and voltage drop at resistance RB, and voltage drop at VBE. So this loop is, I call the B loop. So if everything is a full signal or physical signal, so the total input voltage is VBB plus VS to the left. Then equal the voltage drop at resistance RB. So it's RB times the full current IB plus the full voltage drop between the base and emitter VBE. So the VBE. But then the full current IB contains the DC portion IB and AC portion IB. And likewise, full voltage drop VBE contains the DC portion of VBE and AC portion of AB. And DC portion of AB is what we meant when you deactivate, turn off the AC source. That's exactly at the single point, question point. So that's Q. And to the left, you have this term is constant in time, and this is time varying. To the right side, you have some terms constant in time, other terms dependent in time. So I separate the constant terms. To the left, I have a VBB. To the right, I have a first term, this term, and second, this term. And that equation is exactly what we would derive from chapter 5 if we don't consider AC input, AC source is not present. Okay, so repeat the chapter 5, we should get this equation. What we are interested in is what happened to the AC signal. So the left time varying signal is VS source. The right is time varying part of a voltage drop at the resistance RB, and time varying portion of the voltage drop, voltage VBE. So that's the AC Kirchhoff law. This is a new part we derived for chapter 6, the third one. Another loop goes from the ground to the top, VCC, and going down through the voltage drop at resistance RC, and going down through the voltage drop at is VCE and back to the ground. So that's a Kirchhoff voltage law to the collector emitter loop. So full signal Kirchhoff law is VCC rise equals the voltage drop at resistance RC and voltage drop at VCE. And voltage drop at RC due to the current IC contains two parts, constant current ICQ and time varying ICQ. And VCE contains the constant VCEQ and time varying or small signal VCEQ or AC VCEQ. Not Q, AC VCE. Again, pick up the constant term on the left and constant term on the right. We just come back to what we would derive. Okay, the Kirchhoff law on the DC circuit from chapter 5. The new thing is the AC portion signal. The left has no time dependence. The right has two terms, has time dependence. Okay, small IC and small VCE. So I express in the last equation. So this AC equation are the two equations I derived. Okay, from chapter 6. And I repeat that two equations I derived AC KVL by these two equations highlighted in the blue. Okay, that's mathematically I derived this equation. Mathematically I derived this equation. Okay, can I have more insight? I can have more insight. This is the equivalent circuit. Okay, this is the circuit symbol. Because between the emitter, between the base and emitter loop is this loop. This loop is, the terms by term in the equation is voltage rise Vs equal to small signal voltage drop at RB plus a small signal voltage drop between VB. So exactly is this loop. How about the second equation says, basically small signal voltage drop at a resistor. That's typo. Okay, that's typo. That's typo. I need to correct. This is not RB. This is not. It's RC. So small signal voltage drop at resistor RC plus small signal voltage drop, okay, VCE. So this voltage drop add together is this voltage, okay, this loop. So this one. So these two equations, I can find the circuit simple, okay, representation. You may ask, okay, sure, by the mathematical equation, it looks like you derive this, okay? Any relationship between from this circuit to the original circuit? Well, you look between the original circuit to this circuit, it's exactly the same as what? If I deactivate voltage VBB and once I deactivate voltage VBB, DC voltage, to the left, I have this. Once I deactivate the voltage VCC, and that part is ground, exactly is ground. So that's the exact the same way approach if we use the superposition principle, deactivate the DC source, we come to the AC equivalent circuit. And here I call the AC equivalent circuit as external AC equivalent circuit because what? That's just outside the transistor, whereas the circuitry become what? I have not touched what's the behavior of the transistor inside in AC signal. To do that part, I have to analyze the device law, okay, for small signal. So device law, first, I looked at the base current, and then they operate near the crescent point. And we know the base current is just a p-n junction current. So IB is proportional to some quantity, okay, which is IS. If you determine the IE, you divide by 1 plus beta, that's IB. But important thing is that it's exponentially dependent on VBE and the factor. So that's a p-n junction. And this VBE is time a full signal. So and this IB current is a full signal IB. So it contains is a DC portion and AC portion as well. Okay. So basically, it's we can do the Taylor expansion around this point, fixed point, IBQ, and to Taylor expansion to the first order. Okay. Delta IB, change of IB. And change of IB, I can calculate to the first order by the calculus Taylor expansion. Okay. It's the slope derivative times the change variation of a VBE. So this calculus tells me is this. That's the relationship I derive. Okay, basically small signal variation, okay, around the crescent point, just small signal to the first order, just moving up and down here. And I hate to write, keep writing this derivative expression, so I introduce a symbol R sub pi. So I define one reciprocal of R sub pi exactly is what I meant by the derivative slope. Okay, if I evaluate this slope mathematically, it turns out to be just what? Crescent point base current IBQ divided by the thermal voltage gives you reciprocal of R pi. Okay, so I have this relationship. And so I replace this symbol by 1 over R pi, and I can multiply this R pi to this side. So this side I have what? 1 plus, let's say. So this, I can replace this one by 1 over R pi. But then, variation of the base current really is due to the AC current. So delta IB, full IB, really just AC IB. And likewise, delta of a full voltage change of VBE is small signal VBE. So if you replace this by small signal VBE, replace the delta IB by small IB, and replace this by 1 of R pi, you rewrite this equation by this equation. So what does this mean? That just says it relates to what? AC base current to AC voltage drop VBE by simple resistor. So basically, between the base and emitter is represented by a simple resistor RB. Okay, so we come to the end for this class. Then we'll pick up this, okay, Thursday. Any questions?
I have a quick question.
Yes, please.
For the radio or the amplifier project, is it a team project or is it individual?
Team, your lab team.
Okay.
Yep. Okay. And hopefully the lab team, two of you work in the lab, is just will